I think we can start the talk now. So hi everyone, welcome to the ISGC seminar again. Today we have our speaker Jose, who is also my collaborator. So let me introduce him briefly. Jose did his bachelor degree, master degree, and PhD in from in a, I mean from a year at the year 2014 from the Complutense University of Madrid. Later, he was working as a postdoctoral researcher in the University of Oldenburg from 2015 to 2020 with Professor Jutta Kunz, who is also my supervisor. From year 2020 until now, he's working as a faculty member in Complutense University of Madrid. His research interests includes the gravitational waves from compact objects, such as the black holes and solitons, in particular the ringdown phase, the quasinormals of these objects, and how their signatures can behave in some alternative theories of gravity, such as the Einstein-Gauss-Bonnet theory. So Jose, you can start your talk now.
Thank you very much. Well, first, thank you to the organizers for inviting me to give this talk in these nice seminars you organize. So today I want to talk to you about the quasi-normal modes of some model of black holes. These are black holes in the alternative theory of Einstein-Gauss-Bonnet with a dilaton. And we're going to consider the case where the black holes are rotating, which is the novelty in this work, which has been done in collaboration with Fexen Ku, Burkhard Kleehaus, and Jutta Kunz. You can find more details in this paper. So this is the outline of what I'm going to talk today. We'll start with a brief introduction where I want to explain a bit about the properties of these black holes, because I understand that maybe not everybody is familiar with the properties of these objects, and I think it's important to understand a little bit the features, the differences of these objects with respect what we all know, which is the Kerr model of black hole in general relativity, right? After that, I will talk to you about the perturbations and how to extract from the solutions the quasi-normal modes. Quasi-normal modes will tell you now why they are important for the study of gravitational waves. And we will do that introducing a new method, the spectral decomposition of metric perturbations in this context of perturbations of rotating black holes. With that machinery in place, we will obtain the results, and I will tell you a little bit about the special features we obtain in the spectrum of quasi-normal modes for black holes. And I will finish with some conclusions. If I have time, maybe I can comment a little bit about further applications that you can study with this formalism. Okay, so let's begin from the beginning. Why do we want to study quasi-normal modes, right? Well, the general idea is to understand the gravitational waves emitted from the merger of compact objects, in this case of black holes. No? As you all know, the merger of a black hole generates gravitational waves with this profile, and it can be understood in three different phases. No? The phase where the two objects, for example, the two black holes are spiraling together, a phase more complicated where the two black holes are merging, the horizons are merging, and then you have a third phase, the ringdown phase, where you have presumably an object out of equilibrium, a black hole out of equilibrium, which is radiating gravitational waves and relaxating, right, to a stationary solution, which is presumably a rotating black hole. So each phase can be studied with different tools. For example, the spiral phase with post-Newtonian formalism, the merger has to be done with full numerical relativity, but the ringdown phase can be done using perturbation methods, black hole perturbation methods, in the sense that you can perturb with some set of non-radial perturbations. I will tell you now the metric or the fields that compose the solution, and understand what are the resonant frequencies that characterize this ringdown phase. So this ringdown phase is determined by some resonant frequencies and some exponential damping that can be extracted using the quasi-normal mode formalism. In general relativity, we know that the black holes are modeled by the Kerr solution. This is a unique solution in GR. And the solution is completely characterized by the mass and angular momentum. If it's charged, we have Kerr-Newman, then you have the electric charge. Okay, but the spectrum of quasi-normal modes is completely determined by these parameters. If you have matter, imagine a star, then it will also depend on the matter and the model of matter composing the star. The point is that in alternative theories, typically we have additional parameters, additional couplings in the theory, and maybe extra charges. For example, if you have theories that include scalar fields, you can also have charges associated with new scalar fields. And now your spectrum depends also on these parameters of the theory. So that's one difficulty, that presumably these alternative theories will have a more rich, at least, spectrum. No? Also, there is a difficulty from the point of view of treating rotating black holes. If you consider a static background, well, you have spherical symmetry, and then the perturbation theory can be simplified greatly if you choose the right ansatz and the right gauge, and you can decouple the perturbation equations into a system of ordinary differential equations. Essentially, you can study the problem as an eigenvalue problem, like typically some Schrödinger equation, no, in GR, for example. In Kerr, this is a bit more involved. Now you don't have spherical symmetry, you have axial symmetry, but still in GR, for the Kerr solution, you can find the right gauge, if you want, to decouple the equations into a set of ODEs, essentially. This is done using the NP formalism. Essentially, as you probably know, you can obtain the quasi-normal modes from the Tulkovsky equation. But in general, if you consider metric perturbations of non-spherical backgrounds, the situation is going to be much more messy. It's not going to be trivial to decouple the equations into ODEs, using essentially some kind of spherical harmonics or ellipsoidal harmonics, this kind of thing. So the idea is, can we study the full problem of metric perturbations using or solving directly the partial differential equations? That's a bit the idea. Second, maybe I don't need to motivate it in this audience, but why do we want to go beyond GR where things are so simple? Well, as you all know, we have the problem of dark energy and dark matter from the observational point of view. We also have the problem of quantum gravity from the more theoretical, so that points us to the idea that we have to go somehow beyond the Einstein theory of gravity, right? The theory has to be compatible with experimental tests and theoretical requirements, but in principle, you have a full slew of possibilities of theories that can fulfill in principle, these tests. Very popular are the family of Hornensky theory, Hornensky gravity, scalar tensor theory, FOR, etc. In general, the idea is that Einstein theory is expected to break down, right, at high energies or strong gravity regimes, which is precisely the regimes that we have when we have mergers of black holes, right? So presumably, the modification to Einstein gravity could be detected in principle if we observe with enough precision the ring down of a merger. Okay, so what we are going to talk today is about this theory, this specific theory, the Einstein-Gauss-Bonnet-dilaton gravity. This is a very interesting theory because, well, it has a number of qualities that make it interesting. No? First, it's a higher order correction to Einstein theory that can somehow be justified from string theory. If you take the low energy limit of string theory, typically the string theory gives you these extra terms in the curvature given by the Gauss-Bonnet curvature and some extra field, some scalar field, which happens to be a dilaton field. So from that point of view, it's more or less motivated. It's also quadratic in curvature, which means that the field equations that result from this action are second order, and they also happen to be Gauss-free, so they have these nice properties. Nothing weird is going to happen. In general, we expect them to be well behaved, the wave equations, this kind of things, right? So the action of this theory looks like this. Typically, you have the Ricci curvature as in Einstein. You have some scalar field, right? The kinematic term of the scalar field. And then you have this new term, which is given by the Gauss-Bonnet curvature. And as you can see, it's coupled to the scalar field via this coupling that makes it a dilatonic field. And you see that the theory has, in principle, two constants, the alpha, the Gauss-Bonnet coupling constant, and the gamma, which typically is called the dilaton coupling constant. Okay. The Gauss-Bonnet scalar is the standard Gauss-Bonnet. As you know, it can be obtained from the Riemann scalar and contractions of the Riemann scalar in this way. Okay, this looks easy enough. Now, to study the solutions and the spectrum of the quasi-normal modes, we need to obtain, obviously, the field equations. Here, things become more messy, but the idea is to take this action and obtain the field equations in the standard way. And you get, of course, the generalized Einstein equations, if you want. Einstein tensor equals some tensor that now is not trivial. And of course, you have a new field, which is a scalar field. Essentially, you have the typical equation for the scalar field, some kind of, you want the typical Klein-Gordon kind of equation, massless, with some source given by the Gauss-Bonnet term. Okay. Here in this stress energy tensor, if you want, you are hiding all the complexity of the theory. Now you have the stress energy tensor that comes from the new scalar field, standard, but then you have some contribution for the Gauss-Bonnet theory that it looks horrible, very complicated, but in general, as you can see, it's just is given by the contractions of the curvature tensors with some coupling to the scalar field. Okay, that's a general idea. And from here, you have equations that you can try to look for solutions. Black holes, neutron stars, wormholes, everything you want. Okay. For example, let's focus on black holes to have an idea of the properties. I think it would be nice to spend some time on the simplest case first, the static and spherical symmetric black holes. Okay, these are known since the 90s. Many studies about them. You can propose an answer for your metric, static and spherical symmetric, the usual, and for the scalar field. Okay, the standard, and then you throw this into your field equation, simplify, blah blah blah, solve the equations. It happens that equations cannot, the solution, these static black holes cannot be obtained analytically, or is not known analytically, so the solutions are numerical, have to be obtained with numerical methods. But in principle, it's a set of ODEs. You can use many methods to obtain solutions. Fine. What you can study analytically is the behavior of the solution near the horizon and asymptotically at infinity. I think this is interesting because if you, to discuss a bit, because if you study the behavior of the solution, the metric close to the horizon, you get a number of, and you impose regularity, you want your horizon to be regular, etc. And then you get a number of constraints, a number of equations that come from the field equations, that one of them tells you that regularity implies that this condition has to be satisfied. And this condition looks a bit ugly, but essentially is some quadratic equation in the first derivative of the scalar field near the horizon is giving you a lower bound, because for this to have real solutions for the scalar field, it tells you that this combination of quantities has to be larger than 0. So the basic idea I want to point here is that these solutions have some kind of bound, of some kind of bound where when you saturate this bound, the solution becomes not regular. You cannot satisfy the regularity condition. And beyond that, there are no regular black holes. Okay. At infinity, you can also do some analytical study. And of course, the solution, just to tell you that the solution is characterized, of course, by the mass, the total mass we will have in Schwarzschild. But now you have the scalar field that is, if you want, characterized by the scalar charge. We can call it QD or whatever. And how does the space of solution look like? If you integrate the equation with these conditions, you obtain a number of solutions. And I think the best way to understand how the space of solutions look is with this kind of diagram. For example, here I show you the value of the scalar field at the horizon as a function of the Gauss-Bonnet coupling constant scaled to the mass. The coupling constant has units of length squared, so it's convenient to scale it to the mass of the black hole, right? And then you get this, the solutions nicely stay on this one parameter curve, okay? For alpha equals 0, you have Einstein theory, right? You completely kill the Gauss-Bonnet coupling. You just have Einstein with some trivial scalar, fine. As you increase the coupling, you are increasing essentially you are increasing the scalar hair that the black hole has, right? As you keep increasing it, you reach a limit value of alpha for which no more solutions are found. And the properties around this limit value, which is the limit value I just told you, when this relation is saturated, is quite curious. We're not going to discuss much about this, but you see that you have at some point uniqueness of the solutions is lost, and you can have for the same value of alpha two different black holes with different, if you want, scalar charge, essentially, right? So that's the idea, that the space of solutions, at least when you scale in the mass, is bounded in this way, with some upper limit of the alpha over m squared coupling. Okay. Of course, you can plot this in different. You can study different properties. For example, the area, the same idea. Okay. So what happens? Well, another point I wanted to make: this feature of a limit value of the coupling constant is generic. Remember that we have this other coupling, the dilaton coupling, the gamma parameter. If you increase the previous figures I showed you for gamma equals 1, if you change the coupling parameter, the idea is the same. You have a limit value of alpha for which regularity of the solution is lost. And even if you consider other couplings, very similar things happen. For example, here, if you change instead of exponential function, you have just a linear term in 5. You also have an upper bound for the alpha over m squared value. Okay, so this is generic. Fine. So with this idea of how the static solutions look like, let's go now to what we want to do, which is rapidly rotating black holes. These solutions were first constructed by Burkhard Leihaus, Jutta Kunz, and Evgen Radu in this paper, and later studied different directions in this other paper, right? So the idea now is that you have a background. It's not static, it's stationary, it's actually symmetric, it's rotating. So you propose an ansatz, more or less complicated, but essentially it's the same kind of functions you will expect from the Kerr solution, only that they are obviously different. So you have to leave the ansatz in terms of the two variables, the radial variable and the theta angle, right? And your scalar in the same way also depends on these two variables. Now you throw this into the field equations, boom, 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 you obtain a system of PDEs that you have to solve. Unfortunately, the solution of the rotating black hole is not known analytically in this theory. You have to rely, again, on numerical solutions. Fine. But in principle, it's doable. Details are explained in this paper. Qualitatively, it's the same idea. Now you have to, if you want, you can analytically study how these solutions behave near to the horizon and asymptotically. Asymptotically, as you expect, you have again the solution determined by the total mass of the black hole. Again, you have a non-trivial scalar charge, this QD, and now the solution is rotating, so it has some angular momentum. You can read from the inertial dragging, the angular momentum, or calculate it however you like. Okay. Near the horizon, same idea, more complicated, but you have to impose regularity of the killing horizon. This is going to throw you again some relations similar in spirit to this relation I show you here, more complicated because now they depend on theta. These are ordinary differential equations in theta, but the idea is similar. Your solution is going to be bounded by this condition, and there will be a region of the parameter space where you have regular solutions and another one where they are not. Okay, so solve the equation with these conditions, and this is how the space of solutions look like. What I'm showing you here is the angular momentum scaled to the mass again, and the alpha parameter scaled to the mass. This is for gamma equals 1, the standard Gauss-Bonnet-dilaton theory. And then you generate solutions, and you see that they fit in this area of the space of parameters. What's going on here? Okay, in this black line, you have here the the Kerr solution, right? When J is 0, alpha 0, you have Schwarzschild. As you increase the angular momentum, you increase the angular momentum of Kerr. Eventually, as you all know, you reach the extremality, essentially when J over M squared is equal to 1, right? And you have a degenerate horizon, etc., etc. This is the way GR is bounded, no? The GR solution is bounded. In red, I showed you the static, what I showed you before. You start from Schwarzschild, you increase the alpha parameters, you start to increase the scalar hair of the black hole, and eventually you touch the limit solution, this solution where regularity is lost. And the same happens if you have rotation. Imagine I put a Kerr black hole to rotate with, I don't know, 0.5 in J over M squared, and now I increase the alpha parameter. Behaves qualitatively the same as the static black holes. I start to increase the scalar hair, and eventually I reach a critical solution beyond which I cannot obtain regular rotating black holes in this case. Okay, and the same happens for different parameters or different values of the angular momentum. Surprisingly, you have to the limit in this case is interestingly is given by two different curves. One is the critical where regularity is lost, but you have also a piece of this limit that is bounded by a set of extremal solutions in Einstein-Gauss-Bonnet theory, right? So this is also something. Of course, in the static case, you don't see that because you are in this region. But as you get closer to the region of the parameter space close to extremal curve makes sense now that you can in general continue the extremal curve solution into the Einstein-Gauss-Bonnet theory, right? So that's what happens. Okay, I can show you also how it looks like when you plot the area. Essentially the same idea. What I want to transmit here is that you have this parameter space, bounded parameter space of the solutions, and then you have all these different sets delimiting the boundaries, right? The Kerr, the static Gauss-Bonnet, the extremal Gauss-Bonnet solutions, and the critical Gauss-Bonnet curve. Okay, so with that in mind, I hope this was a crash course on how the space of parameters look like in this theory. Richer, as you can see, than GR. Now the idea is to take a solution, no, in this one of these solutions and perturb it and try to extract from them the spectrum of quasi-normal modes that is going to determine the ring down, right, of these solutions. How to do this? This is where I told you that is in principle you have the complexity that you cannot decouple the equations. You have your solution is actually symmetric, not stationary. In principle, the perturbations of the metric is going to result in a system of PD, complicated PD equations. Linear, because you are going to linearize in the perturbations, but they are still PDs. And in principle, it's not clear if they can be decoupled. So that's not an option. Using, trying to obtain something like a Klein-Gordon equation doesn't look feasible also. So the idea is to, okay, let's attack the problem frontally and try to integrate the system of PDEs that result from the metric perturbations. And to do that, there are a number of methods. The one we are going to use is the spectral method, spectral decomposition. Let me briefly tell you how it works. This is a method that probably you all know. It's used in many areas of physics. Is maybe one of the standard methods to solve PDEs, right? In much more complicated settings than this one, I believe. So the idea is the following. You start, as always, you have your background metric. In this case, imagine you have your rotating Einstein-Gauss-Bonnet-dilaton black hole, and you introduce some linear perturbation of this metric that in general is going to depend on all the variables. You are considering full perturbations. Depends on time, the radial coordinates, and the angular coordinates. Now, what you can do, inspire if you want, from what happens in the static case, that is that in the static case, because you have spherical symmetry and everything is nice, you can decouple the perturbations with different parity. and you can decouple the perturbations that are axial or odd, behave oddly under parity transformations, and the ones that are even, right? And you can formally say that, okay, this perturbation in principle is going to be a sum of these two types of perturbations, but formally they only decouple in the static case. This is the shape they have. If you write it as a matrix, the axial is a bit simpler. You have these four metric functions. And the polar, you have these other metric functions. Because you have axial symmetry, you can always say that, okay, my behavior with the phi angle is going to be this way, a harmonic, introducing an M set constant, okay? And because we are interested in the resonances in the quasi-normal modes, we assume that the time dependence of the solution is also harmonic with this omega. This omega is going to be the frequency, is going to carry the frequency and the damping time of the perturbation. In general, it's going to be a complex number. The real part will be the oscillation frequency, and the imaginary part is going to give us how this perturbation decay with time exponential. That's going to determine some characteristic time that we call the damping time, okay? So now, same as before, you have this answer for the metric perturbations, throw it into the field equations and see what happens. Here, what I gave you is a bit more generic. Here, you can fix the gauge in different ways. You can play with the gauge and see what is more convenient. But in general, you proceed as you will do for the static case. Maybe some of you are familiar, and of course, now you have, the important point is that you have a scalar field and you have to perturb it. Also, the solution, Gauss-Bonnet-dilaton black holes have this non-trivial scalar field, so you have to perturb it to have a consistent set of perturbation equations and hence obtain the consistent spectrum of quasi-normal modes. But this is a scalar, so you can treat it in this way, the perturbation. Fine. Unfortunately, the set of partial differential equations that result from throwing this into the field equations is too complicated to show you here. If you are interested, I can show you. It's very big. But in general, what you have is a system of partial differential equations, linear partial differential equations for this set of perturbation functions. Okay. It's convenient when you treat these problems to compactify also the space, the parameter, the variables. Right? You have your radial variable that it goes, if you are interested in the exterior of the black hole, it goes from the horizon of the black hole up to infinity. So you compactify in this way. Now your x goes from 0, which is the horizon, to 1, which is infinity. And the theta, well, you can also, if you want, define it as the cosine of theta, the y. It's also convenient. This is not so relevant. And very important in the spectral method is always to use a convenient parametrization. What you can use is something like this for the metric perturbations and for the scalar perturbations. This you can try other parametrizations. They all work. You can make all kind of analysis of what is better from the point of view of numerics, more stable. But the idea is that now you have these perturbation functions, okay, that you have to solve in order to so you have a system of PDEs that depend on these unknown perturbation functions, and you have to solve this system of PDEs in order to obtain the omega, no, the quasi-normal mode. From the field equations, you have seven. You can obtain these 7 PDEs, okay, for the metric and for the scalar, of course. And they are linear equations, so maybe they are very complicated. I cannot show you, but the general form is linear. I mean, it's some differential operator acting on a vector where you can throw all these perturbation functions, and this is equal to 0. Okay, in principle, it's a system of linear PDEs. But you have to give some boundary conditions in order to solve the system. What do we want to do? We want to study the ringdown. So what we want is to study gravitational waves emitted by this black hole out of equilibrium. So the physical boundary conditions that we want to impose is that the perturbations are outgoing at infinity, so the object is radiating waves to us, and we have a horizon, so wait, this is wrong. It has to be ingoing at the horizon, the other condition. So you have a horizon and nothing can go out of the horizon. The gravitational wave has to go into the horizon. Then you have this Seppi axis, if you want theta 0 and theta pi. So there, what you have to impose is regularity. Okay. The idea is similar to what I told you for the background. You require that your perturbation functions are regular or outgoing, ingoing at the corresponding boundaries, and you study what the PDEs tells you about the perturbation. And those conditions can be written again as a set of linear equations, okay, in terms of the perturbation functions. So now you have your system of PDEs at boundary conditions at these boundaries. Now the idea is how to solve this, because these are complicated PDEs, especially in Gauss-Bonnet-dilaton, and complicated boundary conditions. So here's where we introduce a spectral method. What you say is that you decompose the perturbation functions in terms of some special polynomials. For example, we can use, here you can choose what you can use, right? We use for the radial behavior, radial dependence, we decompose the solutions, the perturbations in Chebyshev polynomials, and for the angular dependence, we use spherical harmonics, essentially, the Legendre polynomials in this case, if you write it like that. And the principle, of course, you can. This is a good basis. You can formally expand this up to infinity. What we do is to truncate, numerically truncate, to solve the system up to some value of n, where you truncate your sum, and then you have these coefficients that are the ones that you have to obtain numerically. Okay. So in practice, what you are doing is translating the system of PDEs and boundary conditions into a system of conditions for these constants. Okay. What you do in the spectral method is to discretize the domain of integration, and then you evaluate your decomposed PDEs and BCs in this discretized domain, and you obtain a set of algebraic equations that determine your coefficients. So in this case, it's convenient to choose this type of points of Lobato in X and homogeneous in Y. You can make other experiments. The results don't change much with this choice. And what happens if you do that after some manipulations is that you can write the system, as I told you, as a system of equations for the coefficients C up to some value of nx. And this is a system of algebraic equations that look like that. And now you solve it however you like. You can use methods to obtain to solve the eigenvalue problem, the C's, whatever you want. Okay. The complexity now, you don't have PDEs anymore. You have algebraic equations, but you have a lot of equations. The more points you introduce, the higher the order of the decomposition, the more points you have. Okay, so you have to treat all this with care numerically in order to extract from here the eigenfrequencies, not the omegas. But that's the general idea of the spectral method. And as you can see, in this case, we are going to treat black holes, but you can treat other systems as long as you can express the equations like this, or even other forms. But in principle, if you are treating other objects, for example, a star, you no longer have a horizon. You have, if you want the center of the star, impose regularity, can also be written as some set of boundary conditions. Okay. In principle, this method can be used for different objects and can be used, as you see, to treat directly the metric perturbations. Okay? First, some tests. We applied this method to the Kerr black holes to confirm that, yes, we can reproduce the very well-known results, the spectrum of Kerr that can be obtained from the Turkowski equation. That is very simple because it's essentially ODEs, what you have to solve there. So we did what I told you, decompose the metric perturbations of Kerr using the spectral method, and then you study the quasi-normal modes, and you get, for example, here in purple, I showed you the quasi-normal modes of Schwarzschild. If you increase the angular momentum, this is J over M squared. you will get the modes for curve with the corresponding angular momentum, right? And here I'm showing you the real part of the mode versus the imaginary part. This is a very well-known spectrum of curve. As you can see, the method allows us to obtain, for example, if you look at the curve with A0.6, not the blue point, we obtain a lot of modes. We obtain modes with positive values of the real part of omega and negative values of the real part of omega. We also obtain modes, as you can see here, that increase in the imaginary part, absolute value of the imaginary part, it goes away from 0. These are the different excitations. This is the fundamental mode. This is the first excitation, the second excitation. And then as you go away from the omega r 0 axis, right, you have also these other modes. These are the modes that are have different leading multiple decomposition. For example, this is the mode that it has leading L equals 2 in the decomposition in spherical harmonics. In the case of Schwarzschild, the decomposition is exact. So these are the modes that have L equals 2 spherical harmonics. These are the modes that have L equals 3 spherical harmonics in Schwarzschild. When you spin the solution, the composition is no longer true. The decoupling in spherical harmonics. So in general, you have here a mixture of multiples, okay? But still you can talk about leading multiples. So this mode is the one that is leading in L equals 2, L equals 3, L equals 4, and then the corresponding excitation, okay? That's the idea. I insist on that because now when we go to Gauss-Bonnet, we're going to see something similar. So this is the idea, why we have so many modes, right? Okay, the checks, a bit formal to tell you that the method works very well. You can track the different modes with the angular momentum, the real part, the imaginary part for different modes with different excitation number, different L, L2, L3. We can also do different M set, all you want, and check with the modes that you obtain from Teulkowski, which is what I showed you here. You compute the difference, right? And you see that the difference, for example, in the fundamental mode is 10 to the minus 7 or better. As you treat excitations, the difference becomes a bit larger, but still the method allows you to have very good confidence in the results, right, for the excitations. So this is just to convince you that the method works very well, and this is to show you how the perturbation functions look like. Okay, these are the modes, but what you are actually solving is the perturbation functions. The t is a polar function. It's a function of x, the radial component, and y, the angle. And h1, for example, is one of the axial functions, right? And this is to show you how from the behavior of the function, you can also see if a solution has a certain multipolar predominance, and also if you can call it polarlet, meaning that the polar sector of the perturbations is the one leading, dominating the perturbation, or if it's axial-led. For example, for L equals 2 polar-led, you see that the T is dominant with respect to the axial, has a slightly larger value. Okay. While if you go to axial L equals 2 mode, you see that the H1 dominates the polar function, right? So with the same mode, Kerr has isospectrality. I didn't say that, but it's very well known. The fact that Kerr has isospectrality in the sense that L equals 2 axial and polar modes have the same value. Okay, but in principle, in each point I show you here, you have two different modes with the same value of omega, but one has the perturbation functions are dominating in the polar side, and the other one is dominating in the axial side. Okay. That's also an important idea because now when we change theory, that isospectrality, that degeneracy of the spectrum in general is going to break. So that's what I want to show you now. I don't know how much time do I have, sorry.
I think you have 20 minutes. 20 minutes, yeah.
20 minutes, okay, yeah, okay, so I have. So now I show you how to use this method to obtain, or at least to attack the problem, and how it works for Kerr. Now let's go to what we were initially doing, which is rotating Einstein-Gauss-Bonnet-dilaton black hole. So in principle, same idea. Okay, so I don't need to repeat much. You essentially, you have your equations. You decompose the perturbation. You introduce the perturbation with these functions. You work it out to the point that you have a system of partial differential equations with some boundary conditions. Now, these equations are the Gauss-Bonnet-dilaton equations. That's the idea. And you solve the problem in the same way. You decompose the perturbations, solve the coefficients, etc. So what you get is this kind of spectrum, similar to what I showed you for Kerr, but a bit more complicated. Here I show you again the imaginary part and the real part. Okay, this is for a particular solution, a particular set of solutions. Let me explain now. All of them have the scale angular momentum J over m squared, essentially equal to 0.6. Fix this number, m set to 2. And what we do now is to, if we were in Kerr, right, we will have some doubly degenerated mode that will be in the center of this curve. I mean, in the middle of these curves. This will be the Kerr modes, okay? In the center, in between the red and the blue. Now what you can do is to increase, you remember the diagrams I showed you before, the coupling, the alpha coupling. So you start to increase the alpha coupling, and what you can see is how the modes, the axial LED and the polar LED mode for the different multipolar number change as you increase the alpha coupling. Okay, and what you see is that the polar modes go in one direction and the axial mode go in the other direction. So from this figure, different points in I will show you now with more quantitatively what's happening, but the idea is that each point here is for a solution with different Gauss-Bonnet coupling. Okay, this one has a coupling and this one has another coupling, and as you increase the coupling, the axial and polar modes bifurcate and go farther away. Okay. So one first idea that can already be seen in this diagram is that now the degenerate spectrum of Kerr is no longer degenerate. You don't have isospectrality, but you have axial and polar modes with different frequencies in general. Okay, and this happens for all the different multipolar numbers. But you have also another effect here. Remember, you have the scalar field. The scalar field with its own dynamics, the wave equation that result from the scalar field, which is coupled to the metric perturbations, and the scalar field is giving you his own resonances. Imagining the limit of Kerr, what you have is the metric perturbations, and if you are perturbing or introducing some kind of scalar field, you will have some scalar field minimally coupled to the Kerr metric, no? And that will give you some, essentially, the Tulkowski equation for the scalar, right? Now, as you increase the coupling, you are coupling the scalar with the metric, right? And you are growing, in fact, a non-trivial stationary scalar here around the black hole. So you have these new families of modes. That's the idea. You have this family of modes that comes from the scalar, right? And as you increase the Gauss-Bonnet coupling constant, the frequency changes, okay? In some way. Now we will study that with more detail. But the idea is that in Einstein-Gauss-Bonnet theory, you have these three families of modes. The axial and the polar, that of course we had already in Kerr, but they were degenerated, and you also have the scalar modes, okay, the scalar LED modes. Apart from all the multipolar components, and of course you also have excitations that I'm not showing you here, but you also have, of course, an infinite tower of excited modes for axial, polar, and scalar. Okay, so that's the general picture we have now in the spectrum. How to characterize if one solution is polar, axial, or scalar? You can, in general, when you have your rotating black hole with a scalar here, everything is coupled with each other. You cannot decouple polar, axial, and scalar perturbations. They are all coupled together. But what you can study is how these perturbations behave as you go to, for example, the GR limit or to the Schwarzschild limit, where everything decouples. In the Schwarzschild limit, you will have a test scalar in the background of a spherically symmetric solution with nothing. And in that case, you can identify what is polar, what is axial, what is L equals 2, L3, scalar, whatever. And as you start to increase the couplings, the angular momentum, the coupling, the theory coupling constant, you can keep the name, if you want, of each one of these modes, right? And you can see what happens to the solutions, and the solutions inherit the behavior of, if you want, of the solutions in the decoupled limit of Schwarzschild. For example, a polar L equals 2 mode has the T function, which is polar, dominating the axial, this kind of idea. If you have sorry, these are the polar, and if you have the axial LED, the opposite happens. Okay, that's the general idea. And now you can start to do a more quantitative analysis. Here in this very scary figure, I show you a lot of data, but let me break it down a little bit. In the left, I show you the real part as a function of the coupling. In each panel, different values of the angular momentum. And on the right, the imaginary part, same idea. For different values of the angular momentum, how the imaginary part changes with the coupling. Okay. For example, let's look at this one. These are solutions that are all spinning with J over M squared 0 equal to 4, equals to 0.4. And for example, consider the case where alpha is equal to 0. Alpha equal to 0 means we have curve. So in these points here are the curve modes for L equals to polar and axial, as you can see, coincide, isospectrality. Then you have the L equal to scalar, this mode, whatever value, the L3 axial and polar, also isospectrality, L3 scalar, bam. And if you continue, you have more. Fine. Imaginary part, similar idea. Now you start to increase the coupling, okay? As you increase the coupling, you break isospectrality. Maybe here the scale doesn't allow you to see, but the axial and the polar modes are not the same. And eventually the difference between axial and polar become larger. And as you hit the critical value of alpha that I told you before, where the solutions stop being regular, but typically you have a dependence on the mode that is a bit more sensitive with the coupling constant, okay? And the same happens if you take the L equals 3, you see that the difference is a bit large in the real part, and the scale up, typically the frequencies increase, okay. You look at the imaginary part, for example, you look at the L2 axial and polar, you see a little bit the same idea. Initially, for this value of the angular momentum, the dependence with alpha is not very big, but as you move towards the critical value, you see that the imaginary part becomes especially sensitive to the value of the coupling constant. Okay, and in fact, here you can start to think about what's going on in terms of the damping time of the perturbation. Remember that the imaginary part gives you the inverse of the imaginary part gives you the damping time. That means how long lived is each certain component of the perturbation, right? For example, what this is telling you is that the L2 LED axial modes dominate slightly the polar L2 modes, okay, in this region. And of course, it dominates the other ones because the imaginary part is a bit smaller. But as you can see, if you go closer to the critical line, what happens is that the curve of L equals to scalar modes crosses the axial mode. So you have a region of the parameter space for which the L equal to scalar modes are dominating. The damping time is longer, if you want, than the metric modes, both the axial and the polar, you see. And now you can start to study how that works with the different values of the angular momentum and coupling constants, okay? And you see that the phenomenology here is quite rich, right? So depending on the coupling constant and the angular momentum, you have some sector of the spectrum dominating the other. So that's quite interesting, right? It means essentially that the spectrum of the ringdown is going to be much richer, not only because isospectrality is broken, but also, as you can see, some multipolar mode higher multiple mode can eventually dominate the lower multipolar mode. So I think that's also very interesting for the study of the ringdown phase in these theories. Something you can do, there are previous results in Gauss-Bonnet-dilaton theory that use perturbation theory. For example, we have, in the case of Einstein-Gauss-Bonnet-dilaton theory, we have compared our results with the ones from Pierini-Gualtieri using a slow rotation. They use a slow rotation to study the polar modes of the that I just showed you, and we find that our complete calculation is in excellent agreement with their perturbative results. Especially, of course, the smaller the angular momentum is, because the results is for a small angular momentum. As you increase the angular momentum, the differences become larger and larger, but still it gives you a qualitative idea, as you can see, of what's going on. So that's also another test. So let me summarize a little bit the idea. The idea, and I insist on that, is that isospectrality is broken. We have these three families of modes. The ringdown is very rich. We have axial, polar, and scalar modes. But also very interesting idea is that the L equals 2 modes are not necessarily the ones that live longer. As I can have showed you before, you can have L equals 3 living longer, or even L equals 2 scalar. In some cases, L equals 3 scalar. That's a very rich phenomenology in this spectrum. In fact, what happens is that the damping time is very sensitive to both the angular momentum and the alpha, right, the complete constant. And so this has to be a bit treated with care when you model the ring down. So let me finish with some conclusions and further applications, and tell you a little bit more about what we are doing. So this is a new method to calculate the quasi-normal mode of rotating compact objects without further approximations. You don't need to consider a slow rotation or small coupling constants. In general, this method works for the full solutions that are typically numerical, right? And you don't need special gauges or anything. In principle, you can attack frontally the metric perturbations, or you need to fix the gauge, and you can play a little bit with that to try to optimize your numerics. But in general, it's agnostic on what gauge you use. And we have used that to calculate for the first time the quasi-normal modes of black holes in Einstein-Gauss-Bonnet-dilaton theory without further approximations, without linearizing in the angular momentum or coupling constant. We have tested that the results are consistent with previous perturbative results. I just showed you the ones for slow rotation. There was also recently some studies considering small coupling. In fact, in these papers, they use the linear theory, not Einstein-Gauss-Bonnet-dilaton with exponential coupling, but with the linear coupling. But they also approximate with a small coupling, not a small coupling approximation. But we have tested our results also for the linear coupling, just change the coupling and get the results. And our results show very good agreement with the results from these papers. And the general idea is that what I told you already, the richness of the ringdown spectrum. I think that's important because it allows us now to have some more precise modeling of the ringdown phase in Einstein-Gauss-Bonnet-dilaton theory. So far as I know, only perturbative results have been used to model the ringdown phase. For example, in this recent paper also, to treat the ringdown phase, they use the linearized theory with a small coupling constant. So I think it could be interesting to study the full results for fast rotating black holes. And the future, I think, is very bright. This method has, as I told you, applications in all kinds of directions. We are currently considering black holes in other alternative theories of gravities. You can generalize, as I told you, the coupling. You can play with this coupling, the different coupling constants, etc. Introduce additional curvature terms. And as I told you, in principle, the type of object you study can also be treated with this formalism, which, of course, is more complicated. You can consider neutron stars. We are looking into that. Neutron stars have the complexity that you have matter. You have two regions, interior of the star, exterior. So those things have to be treated. Boson stars are a bit more simple. In general, you also have metric with scalars or Procka fields. Well, same idea as I told you. And for wormholes, the same as I told you. In fact, we have applied this formalism to study recently the quasi-normal modes of the rotating Ellis wormhole. This is the Ellis wormhole that probably you all know. It's just the metric coupled to a phantom field, and you can make this the well-known Ellis solution, which is static and spherical symmetry. You can put some angular momentum, make it rotate, and we have used this formalism to study the quasi-normal modes and obtain all kind of interesting results. If you are interested, we can talk more later about it. But yeah, in general, that's what I wanted to transmit, and I hope it was clear enough. That's the end. You have questions, please ask me. Thank you very much.
Okay, thank you, Jose, for the interesting talk. So any question from the audience? Maybe I can stop the recording.